Coming up next, I'd like to introduce Sophie Lebrecht, who is the Director of Operations at xnor.ai, which is a really interesting startup here in the Seattle region that does artificial intelligence on device. And so as they're basically getting this all set up, Sophie, I'll just sort of pull you aside here while they're getting your system set up. Give us your pitch on what xnor.ai does, and am I pronouncing that correctly?
Yeah, you're pronouncing it correctly. And actually, I'm happy to hear what David and some of the other stuff has been talking about this morning, because I was worried about presenting Edge AI at the cloud conference, but it seems like it's a theme. So xnor is really about how do we take these deep learning networks and condense them down so that we can embed them in devices. And in the talk, I'll talk a little bit about how we do that and why I think it's important.
And one of the interesting applications that we've actually reported about on GeekWire is the ability to do on-device image recognition and the ability to use ML and AI there as a way of doing that. And so it sounds like that's part of what you're going to be talking about. Okay, good. So with that, Sophie, why don't you start by telling just a little bit about yourself and your background?
Yeah, so my background is initially in human vision. So how do we see images? I did my PhD at Brown. I then did my postdoc at CMU. And I was really interested in how does the visual system see images? I then sort of transitioned into how do we teach computers to see images? I founded a company in Silicon Valley that looks at emotional image recognition using a deep learning AI platform. And then now at xnor, I'm really kind of focused on how do we take those capabilities and put them in devices so that actually we can see some real world applications. So one of the things that has been interesting in my career is sort of seeing how we go from these very academic algorithms into products that are actually solving real world problems.
And it looks like we're still trying to work out the PowerPoint issues over here, speaking of real world problems. You know, so you heard Mark up on stage talking about Edge. Are you seeing one platform over another, AWS, Google, Azure, emerge as the leader in Edge at this point? Or to what extent would you handicap the race among the three? I'm totally putting you on the spot here, Sophie.
No, it's all right. I would say xnor's platform is the leader. I think, you know, when you kind of take these networks like TensorFlow or Caffe and you try to just make them small, they're still too big. So I think we've got to radically rethink how we're building the architecture for these deep learning models if we're going to deploy them on the edge at scale. And by edge, I mean really constrained hardware and, you know, places where you don't have connectivity to the cloud.
And with that, I'll let you take it away.
All right. Okay, so it's great to be here. So I've sort of given an introduction on what xnor does and what my presentation is going to be about. So I think, you know, we've seen some of this already. I'm sure everybody in this room is really familiar with all of the tasks that deep learning can do. These are just examples in the visual space, but we know we can now do speech recognition, emotional recognition, tons of different things that using deep learning we can train computers to do. But I think, you know, to David's point, 99% of people are still not deploying these algorithms. So we've made this great academic advancement, but why is it that even though we know how to solve these problems using deep learning, that they're not actually making an impact in the products that we have in the market today? And I think one of the reasons is that these algorithms require enormous compute power. So when we think about a full precision deep neural network, we're talking about a 32-bit convolution to even classify just a single image that this image has a dog in. We're talking about billions of floating point operations just to make a single inference. And so, of course, that requires GPU, which means that most people are running these models in data centers. And data centers have become so widespread that actually even Chanel did a fashion show in a data center. So very, very popular. But I think, you know, there are problems that the cloud really can't solve. So thinking about ideas of latency. So if we think about our capability to detect people very reliably, very quickly, now we want to put that on a drone and send it into a natural disaster. now what happens if that model is so big that it needs to be running on a GPU in a cloud? Well, now we're going to introduce latency such that you can't be making real-time decisions. So now, even though we have this capability, it's really bottlenecked by the fact that the algorithm's requiring so much compute power, it's running in the cloud, and we're not able to make real-time decisions that potentially could be saving people's lives. We obviously have talked a lot about privacy. When we think about having cameras in our home, it's great to think about having a smart camera. I have a young child. I'd love to think about having a baby monitor, but I don't want all of that going up to the cloud. People might have elderly care that you want to have a camera in your bathroom because that's where your mom might slip and fall, but you really just don't feel comfortable having that streaming up to the cloud. So how can we take these solutions, get them so small that they can stay on our device? Same is true, in the voice domain. There's a lot of promise around Alexa and these smart home devices, but they're always listening at the moment, and they're always streaming everything you're saying in the home to the cloud at some point. When we think about industrial applications, so I think there's a million different things that different factory operations can do in order to take, very mundane tasks off humans to make it more efficient, but it's expensive and it really becomes a cost trade-off. Even though I could do it, why would I do it? It's too expensive. So I think in order to see these applications, we really need to start driving the cost down. And then this is an interesting one. I know that typically everybody has thought about cloud as the solution to scale, but when we really start to get into the amount of decisions and inferences that these products would need to make, you could think about a smart traffic light. If you have a traffic light at every intersection, on every street, in every part of the world, and you're streaming up to be able to make a decision or an inference, that just takes so much bandwidth and so much network coordination that really I'm not sure that the cloud could scale to those needs. So, just to summarize, I think that a lot of the real world products that we're looking at, first of all, are getting smaller. We're getting doorbells, we're getting glasses, we're getting watches. The hardware on those platforms is also becoming lower cost. So in order for these products to be mass market, we can't have a GPU on every device, and yet the expectation is that every device is going to be smart. We also know that there are situations, in our industry, freight, shipping, we talked about drones and emergency response that really can't even connect to the cloud. So even if that was a solution, and even if scale and latency weren't an issue, there's going to be instances where you need to make inferences and you cannot connect to the cloud. So the question that we really focus on at XNOR is how can we bridge that gap between traditional cloud-based networks and these everyday applications so that we can start to get the products into the hands of real businesses, as David said, into the 99%. So as I mentioned earlier in the talk, deep learning requires massive compute power. So when we're looking at a traditional network, we've got in 32 bits, we're talking about millions of operations. So what if we address this part of the algorithm head on, and instead of making it 32-bit, we try and drive it all the way down to 1 bit? So is there a possibility that we can train a convolutional neural network in binary? So what that would mean is instead of having real numbers and instead of having arithmetic operations, we can actually take two binaries and make it an XNOR gate. So why would you think about training these networks in binary? Well, the first thing is, for anyone that knows stuff about hardware, binary is really suitable to any commodity CPU. So if you have a binary representation, it's really easy to read through the pop count, which then means that you can start to run these algorithms on very low-powered battery devices. It becomes easy to implement on a variety of hardware. So what happens if you just naively say, okay, I'm going to take my real-world numbers and then I'm going to just threshold them so that I can create binary weights? Well, unfortunately, it doesn't work. So, your precision goes way down. So this is on the left of this graph is an example of accuracy on a full precision network. And if you just naively binarize the weights, you get pretty much nothing. So this really requires us to sort of rethink the whole paradigm. So what a lot of our engineers at Xnor are doing is really rethinking how do we train these networks in binary? So how do we take a full precision network with real numbers, and how do we do sort of forward pass and backwards pass and a custom loss to really make sure that we have an accurate representation of the model, but in a much, much smaller network. So when you do that, it's just going to take a while to boot up. This is what we call our $5 deep learning machine. So in here, we're running a full precision, we're running a state-of-the-art person detector. So it's going to take a few seconds to boot up, but it has a camera on, it has a speaker on, and it can basically detect people. So in a minute when it loads, there we go. So the point of this, and I have a demo on the iPhone that I can show you. Okay, I need to turn it off. I have a demo on the iPhone, which, I'm happy to show afterwards. I think, we can run things radically, like faster, smaller, in airplane mode, using only the CPU of the device on the iPhone. But I find that this is incredibly compelling because this is really running a full AI model on a $5 Raspberry Pi. So it really shows that for businesses that feel like the barrier to entry is so high because I need custom hardware, I need AI expertise. Actually, when you look at these much smaller models running on this, now suddenly a whole world of opportunities opens up for people to have very fast, very scalable, private AI models that are running on low-cost hardware and are not requiring the cloud. So just to dig in a little bit into the numbers, just to show you, so what you can see is there really is no significant drop in accuracy. So I think, as I said, the naive solution doesn't work. At first, when we first pioneered this approach, we were seeing a slightly, Mohammed, our CTO, published this paper a few years ago at CVPR, and I think maybe there was a sort of 5% drop in accuracy. And then over the last couple of years, we've been really working on optimizing those retraining algorithms. So now we're seeing a non-significant drop in accuracy, but a huge boost in terms of speed, memory, efficiency. Just to kind of give you some other benchmarks, so other companies like Google are obviously trying to make smaller networks, but you can see compared to MobileNet, we're almost half the size and slightly more accurate. So, when we think about, okay, how do we sort of take these advancements in deep learning and actually sort of apply them to real-world products and real-world problems, I think that the next wave of sort of successful AI really needs to be designing algorithms with hardware in mind. So how do we construct our network? How do we optimize it? But how do we think about the computer architecture that we're embedding it on? And all of those things should be constantly iterating and working in parallel. So when I think about sort of the future of, why does this matter and how is this going to solve all of these problems and how are we going to deliver on the promise of AI to do all of this great stuff? I think, we need to think about the problem. What is the problem that we're trying to solve? What is the AI task that's going to be able to solve that? How do we understand the constraints that we're operating under? And then now can we develop an AI light model, or binary would be one example of that, embed it in the device in order to solve the problem. And with that, maybe we will live in this beautiful private smart home where we have the promise of AI helping to support our lives in a variety of areas where it's affordable, it's safe, it's private, and it's not draining all of our battery and all of our internet. So with that, I want to especially thank Mohammed, who did a lot of the research that I presented today, Ali, our co-founder and CEO, and the entire Xnor team, and Paul Allen's Institute for Artificial Intelligence, where we're currently incubating.
questions at the beginning. We do have a little bit of time, Sophie. Is any questions for Sophie on things? Do you want to go ahead and just step up there? And yeah, there you go.
So what's the product output, so to speak, of your company? Are you going to publish or make available pre-trained binary models that people can then incorporate? And that's what it'll be for sale, right?
Yeah, so if you go to our website, there's a video sort of describing this, but essentially what we're launching in the fall is a web-based self-serve developer platform where you can go and say, what is my task? What is my device? And then what are the constraints? So how much CPU space do I have? You know, a lot of these models are a trade-off between speed, accuracy, and memory. So you can kind of set your parameters and then be able to download a very simple object file that you can then put into your app. And that will be coming out in the fall. And I didn't see that question.
By the way, David is still here as well, too, and especially since he had to cut his talk short. If there are any questions on his talk, let me give you the mic here.
Yeah, can you talk about where you are relative to the gaps that we are still seeing in the autonomous vehicles, the ability to detect and also predict movement?
So, you know, I think what's interesting, so our performance sort of on accuracy is what I would call state of the art, but I think what's really interesting, and we have been working with some autonomous groups, is the fact that now you can have a $5 camera that's able to detect things. So we've been doing some work both inside and outside of the car. And I think, you know, we're seeing great results. We're seeing some good traction. I think obviously for fully autonomous, there's a long way to go, but there's a lot of pieces that I think we can start checking off. Is the person got their seatbelt on? Has anything been left in the vehicle? Is the road condition changing? And, you know, when we think about it, I was actually with a group of autonomous people last night, and they were saying, you know, to deploy the system might be $40,000. So now thinking about, okay, well, I have a $5 device that I can put in multiple areas of the car inside now, suddenly makes it like a realistic solution.
Hi, Sophie. This was a great talk and great concept. What is your current error rate for the people detector? Like, can it view a big animal as in people, or what are the current constraints that you have?
So the people detector was just one example. So the founders of xnor also developed YOLO. I don't know if you're familiar with that. So, you know, so we can run YOLO, and I have that running here, which has 80 categories. So, you know, we, again, sort of what the accuracy depends on what's the baseline, what's the benchmark, what's the task, what's the constraints. I think, you know, we're certainly seeing like state of the art, and, you know, we can extend up to 80 categories. I think, you know, one of the things that's interesting as I think about sort of what the algorithms can do versus kind of what is the use case is thinking about ideas of co-training. So how do we take these and then really kind of drive home performance on maybe 10 more relevant categories? So I'm sorry, it's not an exact answer, but it's like we're in that range. And I think one of the things that I'm excited to see about the platform is that we'll put that capability into the hands of the user or developer to say, you know what, I only need 5 categories, but I cannot fail on them, and I can compromise speed and memory or other things like that.
So is your focus purely offline, or are you also looking at augmenting this binary classifiers, or not classifier, but binary deep learning with potentially other cloud-based or some sort of a hybrid model?
Yeah, so when we sort of initially thought about our go-to-market, there's an obvious application for cloud. So you can basically take this model, and instead of having to reserve a GPU, you can reserve a CPU and get about a 10x saving in cost. So there is definitely the opportunity to use it like that. I think when we thought as a team, are we as a small company going to go after the cloud-based AI people? We decided probably doesn't make the best business sense, but I think as we kind of scale and as we diversify, I think that's something we will consider. I think the other reality is also, you want these networks to get better and optimize over time. So I think, yes, running on the edge, and if the edge is all you have, then we can deploy a model there. But the reality is a lot of our customers will then sync with the cloud, retrain, further optimize so that we can continue to enhance performance.
Hello. So in his presentation, Carlos Guestrin has mentioned that TVM will basically provide an opportunity to optimize for any hardware, so your models and your algorithm are hardware agnostic. And what you are saying that you think the future will be when you design your algorithms around a specific piece of hardware. So how those two ideas work together? Is there a potential for synergy, or those are controversial?
Yeah, I think I do think it's synergistic, because I think at the highest level, the point is we can't ignore hardware. So we can't be designing algorithms in isolation. And so I think, these are different ways to address that. So I think, Carlo's approach of, let's have a platform to make that easy to port onto different hardwares is one way. I think, where xnor's platform will be even more self-serve is sort of, there's not a huge number of hardwares in the world. There are some and they're growing, but we have already integrations with a number of them. So for people that don't want to deal with that, they'll be able to kind of take an algorithm and they'll be able to take a task, specify a hardware, and just get the model. So I think at the highest level, it's like everybody is just kind of moving in the direction of we can't ignore hardware anymore. We need to be embedding these algorithms, and how we do that, I think there's going to be multiple different approaches for multiple different developers that have different appetite for, do I want to be building my own network? Do I want something more plug and play? Does that kind of answer your question?
So my questions can kind of continue over his question. So for all this time, we have been trying to abstract codes. We build containers. We build a cloud service. We try to write the code once and run it everywhere. But you were talking about is we probably design the algorithm around the hardware. So does that mean we have designed everything from scratch, or the previous approach, the abstraction approach, does or does not work, or what's your vision of the future? Well, which approach should we take? Should we redesign everything from scratch, more focus on hardware?
So I think it probably depends on what you're trying to solve. So if I think that our focus is obviously on the edge and embedding it in devices, but I think if you're working on the cloud, you're not going to have those constraints. I think, what's interesting to me, and this is just kind of intellectually interesting, I'm not sure if this is exactly where the field is going to go, but, we kind of take a binary representation, and that works pretty well with commodity CPUs. And I guess what I was sort of hinting at is, okay, but now if we start to look at what the next generation of silicon is going to look like, not that necessarily the algorithm is going to define the silicon or the silicon's going to define the algorithm, but just kind of even having that conversation so that it's not a surprise. Like, oh, I engineered an algorithm in the cloud and now I want to put it on a device and I haven't really thought about, am I really pushing the limits of what that optimization means?
Thank you.
All right, great. Thanks, everybody. Great questions.